So good morning, everybody. This is a work that has been done together with Ognan Oreshkov, at that time a postdoc in our group, and Fabio Costa, who is sitting in the last row here, and is supposed to receive his PhD degree on Monday. So let's see. So as it was announced, I'm going to talk about quantum correlations with indefinite causal order. So quantum mechanics faces us with certain difficulties whenever we insist on the worldview, on objective worldview, according to which physical properties exist prior to and independent of our measurements. So Bell's theorem or Kochen-Specker theorem have been proven and experimentally demonstrated to many different properties, like spin of a particle or position, momentum of a particle. Yet there is one feature of the physical reality that preserves its objective status, even in quantum theory, and that's the causal order. And so that's maybe the best illustrated by looking at the correlations in quantum mechanics. If we think about some events embedded in the space-time, that there is always a definite causal order between these events. So look at this event A and B. This is a time-like separated interval, and we say A is before B, and operationally means that A can signal to B. Similarly, we can think about the events that are space-like separated, in which case these two events are causally neutral. You can neither send a signal from A to C nor receive from C. So what would be kind of a motivation to look at the situations when even the causal order is not well defined? So let's think about the following situation. There are two events, and if we talk about space-time distance between two events, we have to specify a metric. So here this is illustrated by putting Earth on the right, closer to the event B than to event A. But likewise, we can think about the situation in which the situation is just the opposite, where the Earth is closer to event A, and we have a different definite metric. Now imagine that these two situations actually arise from the following physical conditions. Namely, we have an Earth, and we have a super beam splitter that can put the Earth in the two possible amplitudes of the Earth in two possible positions, in which case we will have to say the space-time distance between A and B is not well defined. So that's kind of motivation, why I'm interested in that kind of questions. And currently, we do not have a functioning theory to deal with this. So let's look at the outline of the talk. First, I will introduce a framework for quantum mechanics where we do not assume a global causal structure. And this will also include all possible situations which are familiar with, in which the causal structure is definite, as it is in the standard formulation of quantum mechanics. Secondly, and that's most interestingly, I will talk about correlations that defy causal order. So I will show a new type of correlation in which the causal order is not definite. And in order to show you that this is so, I will introduce a certain causal inequality, which is a reminiscent of a Bell's inequality. And a causal inequality is satisfied by all causally definite situations. Yet these new correlations will violate this inequality. And finally, I will just mention, not going into any detail, that in a classical limit, causal order always arises, which might indicate that space-time and causal order is not the fundamental feature of the world. So let us repeat it again. If we have a space-time, then the causal order is well-defined. And there are two typical situations that we face in our experiments. One when the two observers, Alice and Bob, are space-like separated, and they, for example, share entangled state. Then there is no signaling because the laboratories are space-like separated. These situations are causally neutral. The second situation is in which we describe quantum channels, namely when we have one observer in the past of the other one, and where signaling is possible, for example, from Alice to Bob. But this signaling, and this is important, is only one-directional signaling. It's always from the past to the future. So if you have an assistant entering each laboratory only once, you can have signaling only in one direction, from the past to the future. What do I mean with signaling? I mean really operationally. There are two observers. That's the usual situation that we deal in quantum information, for example. And there are two types of variables. X and Y are something which we call measurement settings. That's what Bob and Alice can control. The putting of one of the other setting depends only on their free choice, or this is some kind of statistically independent variable, independent of all other processes involved in the experiment. And then there are A and B, which are measurement outcomes. The whole situation is described by this conditional probability to obtain the outcomes A and B, given that the choices of measurement settings are X and Y. Now, what it means, signaling, is that, for example, a situation in which we do not have signaling from Alice and Bob, from Alice to the Bob, is that the Bob's experimental situations and distribution of probabilities for his outcomes are independent of whatever Alice does in her laboratory. For example, choose the measurement setting. The opposite situation would be, in which we see that by the choice of the measurement setting on Bob's side, we do change probability distribution or even the outcome on Alice's side, and that will be the signaling. And more formally, one directional signaling means that, appropriate for the example that I have chosen, that if we look at the Bob's marginal distribution, summing up all outcomes over Alice's side, the marginal distribution depends only on the local setting on Bob's side, not on the local setting of Alice's side. However, if we look at the marginal distribution of Alice's side, summing up Bob's results, there is a signaling because this marginal distribution depends not only on the local choice of Alice's setting, but also on the choice of Bob's setting. So that will be one-directional signaling. And if these local marginals depend always on local settings, it's no signaling distribution. Okay, that's what we face in quantum mechanics. And now we can ask ourselves, could we go beyond that? Now, at the end of that, I want to have something which is more general than what we have in a standard quantum mechanics. Now, one possibility is to think that there are actually two-directional signaling. And this two-directional signaling actually might be possible to realize in some solutions of the general relativity, namely in so-called Golden universe, in which we have closed timeline curves. So closed timeline curves would be the situation in which, for example, the Bob can send the information to Alice's past, but Alice can similarly send information to Bob's past. These situations, although they are allowed by general relativity, face certain logical inconsistencies or, let's say, problems related to, most of you know, grandfather paradox. In order to illustrate this paradox, let's assume that Alice performs a NOT operation, a bit flip, in her laboratory, whereas Bob performs nothing, identity operation. And let's now start with a bit value 0 entering Alice's laboratory. Now she makes a bit flip, changes this into a 1, sends through the identity channel to Bob. Bob does nothing. 1 comes out of his laboratory, but 1 is different than 0, and that's the logical impossibility. And also related to grandfather paradox, if you identify, for example, 0 with do not kill Alice's grandfather and 1 kill Alice's grandfather. Now, there were some proposals to overcome these difficulties in quantum mechanics, like the one by Deutsch and by Bennett, Schumacher, Svetlichny, Lloyd, CTC-like structures, but they are all nonlinear extensions in quantum mechanics. So strictly speaking, they lose the main feature of quantum mechanics, linearity, and that's what I would not say it is a solution in quantum theory. It's going beyond quantum theory. Now the question is, can we preserve the linear structure of quantum mechanics, be free of paradoxes, and yet have more general causal structures than what we know so far, namely one-directional signaling or no signaling at all. And that's what our actually framework is about. So let me introduce this now framework. The main key element of this framework is so-called closed laboratory. What I mean with this is that there is an observer, closed, shielded outside of environment, and except for two events. The one is that when a system enters the laboratory, we have some kind of input into the laboratory, then we get some classical data. We perform, for example, some measurement, get some result J, and since we might want to communicate with somebody else, we may prepare the state and send this system out of the laboratory. And so there are these two events, entering and exiting of the laboratory, when the laboratory interacts with the environment. But in between, it's completely shielded out of the environment. There is no side channels. There is no hidden signaling traveling around, and so on. So this is the only way how each party interacts with the outside world. At the end of the day, I would be interested in correlations. That's why I draw here two laboratories of this same type, two possible outcomes. However, I will not say anything about the causal structure between these laboratories. And in particular, I will not assume that there is any pre-existing time shared by these two laboratories. So in a sense, I don't know whether Alice transformations are performed before or after Bob's or whatsoever. And what I want to obtain is at the end exactly the situations in which this is not well defined, who is before whom. Okay, so that was a general picture and a main ingredient of the theory. But now what is the main premise from which I want to derive this framework? The main premise is that local descriptions in each individual laboratory agree with quantum mechanics. So in each laboratory, there is just the same quantum mechanics as we know like right now. This means, in particular, and that's the main point when it starts to be more formal, is that the transformations are so-called complete positive trace non-increasing maps. So this is the most general quantum operation that I can perform in the laboratory. And I denote this by MJ, J meaning a particular outcome has been observed. So this is a map from the space of linear operators on a input Hilbert space H1 to the space of linear operators over the Hilbert space 2, which is the output Hilbert space. These two Hilbert spaces could be at different dimensions because I might lose some particles or get some ancillas and so on. And the second interesting map is so-called complete positive trace preserving map. That's a map when I add up all possible outcomes, and when summing over all these non-increasing, I get finally the one which is trace preserving map. Okay, so what I want to do is to look at the correlations. That's why I look now at the two or even more parties. You have now more indices, more Hilbert input and output Hilbert spaces, and two possible outcomes, JA and JB. And at the end of the day, I want to talk about correlations. I want to know what is the joint probability to obtain a particular outcome on Alice and Bob's side, and the probability for that here illustrated by this probability for the map MA and map MB. Now, we need to characterize these probabilities. If we can characterize this, we have a theory. We can apply this in any situation in which even we do not know the causal structure between Alice and Bob's operations. Now, instead of working with maps, I would like to work with matrices. It's just easier to do it. And there is this well-known Choya-Mikulski isomorphism that connects actually every CP map between these two Hilbert spaces onto a positive matrix on a tensor product of these two spaces. And the people in quantum information use this very heavily. It's a very neat isomorphism. So if you have a map, then you take a maximal entangled state, which is just correlation over really correlated results II, one of those maximal entangled states, and you apply a map only on one of the parties, And then you get a density matrix, a positive density matrix, which represents these CP maps. So in whatever I will say in future about the map, what I have in mind is now that I work with these positive matrices. So that's more formally how you take the map, apply on the maximum entangled states, and obtain the density operator. So now I have the same situation as before, but I do not talk about maps. I have these Choyer-Markovsky matrices represented the two maps. And I again want to obtain some probabilities. But I want to have to be in as close as possible to the quantum mechanics, yet be more general to incorporate situations of indefinite causal orders. And meaning that close as possible to quantum mechanics, I mean I want a linear function. And in that case, if I talk about correlations, I want a bilinear function of the CP maps. These probabilities has to be a bilinear functions of these CP maps. Now, a way how you introduce bilinear functions is if you think about these CP maps as being some kind of vectors, then always a scalar product between this vector and the dual vector gives you a linear function. And scalar product in terms of matrices, a trace between matrices. So I have these CP maps, local CP maps, and then I have a new object, and this new object, in addition to the Choyer-Markovsky representations of CP maps, is something which I will call process matrix. And this is the most important element of the whole theory. This is the element that, through the trace rule, gives rise to the probabilities that I want to characterize. So again, if I'm able to characterize the process matrices, then I will be able to characterize these probabilities themselves, and that's my goal. Now, how to characterize? What are the conditions I want to impose on these W or process matrices? Well, I want them to give rise to the probabilities. I want probabilities to be well-defined. Probabilities to be well-defined means to be non-negative. And indeed, if you require that these probabilities are non-negative, even then, when Alice and Bob share entangled states, you will get that this W matrix has to be positive. And we do allow Alice and Bob to share entangled states because entangled states are non-signaling resource. Even having this non-signaling resource will not fix the causal structure, will not tell us whether Alice is before Bob or Bob is before Alice. So we do allow that, and at the end of the day, we get a nice mathematical condition that these W matrices are positive. Secondly, I want then when I sum up over all results, the probabilities give 1. That means in this language, more formal language, that probability is 1 for all these complete positive trace preserving maps. So it means that in a special case, when I sum up over all results and get complete positive trace preserving map on Alice and Bob's side, the probability must be 1. This is the statement because this is expression for the probability. And the lower line is just the conditions for the maps to be complete positive trace preserving. It's not important right now, but for completeness I wrote down. So these two conditions actually reduce or somehow give a characterization of these W matrices. And now, 5 minutes until the end of the. Sir? Okay. So if you want to generalize this, if you want to characterize these W matrices, then you can W matrices represent in a certain Hilbert-Schmidt basis, and consider those parts of the bases in which you have non-trivial population only of the, for example, input A1 Hilbert space as type A1. Or if you have non-trivial population of the input and output of the Alice Hilbert space, then you will call this type A1 and A2. And this is the only W's that are possible, namely those W's that either describe states, channels, or channels with memories. And since I will go into the next slide into detail of them, I will not now explain these terms right now. So these are the possibilities for the W's. Namely, if W, or process method 3, has this non-trivial part into the input of Alice and Bob laboratory, then this can be explained or understood as a usual situation in quantum mechanics in which two parties share an entangled state. For example, they have a source. The source inputs into the two laboratories. This is A1 and B1, non-trivial input. And then they will be measured or processed in the laboratories. In this case, when you have such a W, any input into your probability expression, you get the usual probability for measuring entangled states. The second example is if you have a channel. So you send the state into the Bob laboratories, then you have a channel from Bob to Alice, and then Alice performs some operation. And this process could be explained by entering B1 state channel between Bob and Alice, an identity. And again, the formalism is rich enough that when you apply these formulas, you get the usual expression for the probability of having a state in entering Bob's laboratory, performing some operation on Bob's side, having a channel, and then finally performing the operation on Alice's side. And similarly, it's a channel with memory, which is the most complicated situation, and the situation in which you have a state, and one entangled state, and one part of entangled state enters Alice's laboratory. The second part goes and waits until the output of the Alice laboratory is re-merged, and then everything's sent to Bob. And that's the most general situation in quantum mechanics that we face. And all these three cases that I have described are actually causally ordered situations that we do have in a standard formulation. Now, let me now divide this W into two rough groups. The one group is this situation when Bob cannot signal to Alice. That means either Alice can signal to Bob or they share non-signaling resource, right, entangled state. And the second group is this group where Alice cannot signal to Bob. Now, we can think about the probability mixture of orders processes in which we mix some of the W's from the first and the second group. And we might ask ourselves, is everything what we have in the nature exactly of this form? Because if it is, then everything in the nature will be in a definite causal order or a mixture of different definite causal orders. And surprising answer is no. And that's the most important part of this whole framework. And in order to give you some operational view or convince you that the no as a possible answer is meaningful, I discuss a certain game. And this game, you will see, can only be win with certain probability if you have W's that have indefinite causal order, that are not of this form as a classical mixture of definite causal orders. So here is the game. It's guess partner's input. That's the game which is actually known in quantum information. Alice is given a bit A, and Bob is given a bit B. And now Alice needs to produce an X, and Bob needs to produce an Y, which are their best guesses for the value of the bit given to the other. Now, a game is slightly more complicated because Bob is given an additional bit B prime that actually tells him whether he should guess her bit, for example, with B prime is 1, or she should guess his bit when B prime is 0. So what it means, like if B prime is 1, then he, with his power, should do his best, whatever he can, to try to guess her bit, to try to receive information from Alice. And if B prime is 0, he tries to make some strategy to send information to Alice, because she should guess his input bit. And now the probability for correct guess, the cost function for the game is 1/2, because B prime is randomly distributed. Probability that she guess his input bit when B prime is 0, and he guess her input when B prime is 1. Now, the game is very easy to explain. What is the classical, actually, what is the highest probability in any causally ordered situation. This is one causally ordered situation. L is in a definite past of Bob. They share a joint time. And now Alice received some information, gets some system into the laboratory, and tries to guess Bob's input. But Bob is in the future. She can't guess. She can just give a random answer. Then she receives her bit. This bit she can send to Bob. Bob can guess now with certainty the bit of the Alice, because he receives that. And then he receives his bit, but this is unimportant because Alice was in the past and cannot guess something what he will get in the future. So that's why in the case when B prime is 1, he can guess with certainty. This is the probability 1. But in the other case, she is in the past, so she can only randomly guess. And altogether, this gives 3/4 for a probability of success. And now I want to tell you a miracle. Now, there is one process, W, that can beat this. And I can give you this W. I can write it down, but you will not understand anything from that. And I can explain the whole process. And this you can find in the paper. But I will try just with 2 minutes, taking from the, no? It's not, eh?
28.
This is not 28. Wait a minute. It's 26 in my case.
Your watch is wrong. It's 28.
Okay? So I will then finish with explaining this, and will not go further. So the idea is that Bob, in his laboratory, has a power to choose what to measure. And now, if B prime is 1, he measures his input bit along the z direction. By doing that, he actually, because here the B in this process, which is an indefinite causal order process, B1 is sigma x. He will annihilate this. When you multiply the trace rule with sigma x and sigma z, his choice of measurement, he will annihilate this. That's a formal thing. But what he will do with that, he will actually leave this open, and this describes the channel from Alice to Bob, because it connects A2 with B1. You arrange very well, yeah. And if B prime is 0, he will do just the opposite. He will measure along the sigma x and annihilate this, because here is sigma z along in the B1 Hilbert space. And in that case, he will open the channel with memory from Bob to Alice. So that's the key thing. Depending on his choice, he can end up after or before Alice with certain probability. And since the game is to either to guess the partner's input or to send your own input, this allows him to adopt his strategy depending on what he needs to do. So you see that in these situations, it's not well defined who is before whom. It's not defined what is the past and the future. And Bob, by measuring his system, can then project this process into being in a definite past or being in a definite future of Alice. Just these two situations. And that's what allows him to be over the 3/4. So I'll skip the conclusions and make just one additional remark in one sentence, that this is not two-way signaling. At no point of this game, you have a closed time-like curves. The flow information is always in one direction. But in which direction, it's not defined until the measurement has been finished. Thank you very much.
All right. We have time for maybe one question or so. Anyone? Howard?
So do you think this has an application to understanding closed time-like curves, or or it's just completely speculative as to what it might correspond to in the world?
You mean less speculated than closed time-like curves? Or? No, it has for time-like curves, there is importance of this, and actually negative. In fact, when you looked at terms which are not allowed, which do not give probabilities which are positive, or when you sum up all results, do not give probabilities equal to 1, these terms in the processes that are not allowed exactly correspond to closed timeline curves. So local loops or global loops when you have flow information between all of them. So in a sense, they exclude, but not ad hoc, not a priori exclude these cases. Excludes because they do not give well-defined probabilities.